So, all right, so today we'll be looking at chapter 5. And the sole purpose of chapter 5 is basically dealing with how do we name compounds based on their formulas, and vice versa. If you're given a formula, how you get the name, and if you're given a name, how you would derive the formula from that, right? So I think I mentioned this in the videos that I've posted, that there's an organization called IUPAC, which stands for International Union of Pure and Applied Chemists, right? And I think they're based somewhere in Europe. And there's a division of IUPAC, which is responsible for coming up with rules for naming compounds, right? And they meet, I think, every couple of years as a committee to work on that, because basically every year new compounds are being made. And what happens from time to time is that there may be changes needed in terms of the rules in order to accommodate the new compounds that are being made, right? So that's basically the rules that we're going to look at here is basically the rules that were formulated by IUPAC, all right? So the first group of compounds that I think I discussed in the videos are compounds known as binary ionic compounds. Binary ionic compounds, right? And as the name suggests, binary means that they're made up of two elements, right? And because these are ionic compounds, one element must be metallic and the other element must be non-metallic, all right? So that's true for all binary ionic compounds, all right? Now, when it comes to naming them, according to the rules, right? Let me see if I can briefly summarize the rules here. According to the rules for naming binary ionic compounds, the first element must be the metal, and its full name is indicated or used, all right? So that's the first thing. The first element in the name and also in the formula, as you're going to see, must be the metal. The second element, which of course will be the non-metal, I'm going to word this now. Stem of its name, I hope I'm articulating this right. Stem of its name is used, followed by the suffix IDE, right? So basically when you're naming binary ionic compounds, you're going to use the full name of the metal, which should be indicated first, and then you're going to use the stem of the name of the other element, which is a non-metal, followed by IDE, all right? So a good example of this would be sodium chloride, all right? So sodium, of course, is a metal, so you're going to use the full name of that element. Then the stem of the name of the other element, so the other element is chlorine. You're going to say chlor, right? Not chlorine, but chlor, and then you end it with IDE, all right? Let me see, another example would be, let's say aluminum nitride. Aluminum nitride, right? So again, first name, full name of the metallic part of it, right? Aluminum, and then nit, right? Which is the stem of the name of the other element, and then IDE, All right, so that's basically how we name the, how we arrange the name of the particular binary ionic compound. Now, when it comes to writing down the formulas, what you can do, and in fact, what I would recommend that you do, is that you use a table that I provided for you in Canvas. So what I'm going to do is clear this here and show you what part of the table I'm referring to. So let me go to files, or let me go here. And then let me go to tables. And then let me go to tables chemistry. And let me download that. Okay, so this is the table here. And what I've done in putting together this table, what I've done is that I've included 3 pages which contains lists of common ions, right? So one of those pages would be this, right? Let me just turn it around so that you can see. Right, this gives you a list of the common ions here in the monatomic ions here in the periodic table version here, and then we have some common polyatomic ions here. And then I've included another page which gives you a list of common ions as well. And then there's another page I've included. And the reason why I gave you 3 of those is because there are some ions that would be in on one page that would not be in another page. So I just decided to just put these all together in the same document, right? So this is a table that you can utilize in order for you to determine the formula for a compound. So going back to the sodium chloride example, so remember I gave you the sodium chloride example, right? If you're asked to write down the formula for this compound, then what you do is you consult the table and you look for the formula for the sodium ion. And if you look it up, you're going to see that it is Na plus. And then you look for the formula for the chloride ion is Cl minus. Now in this case here, whenever you're trying to write down the formula, you have to ensure that the formula represents a compound that is electrically neutral. And what that means, therefore, is that the total number of plus charges must be equal to the total number of negative charges, right? In this case here, that's the case. You have a +1 charge here, you have a -1 charge here. So all you have to do is put them together and you're going to end up with this as your answer for the formula for sodium chloride. All right? And that's it. Now, the other example, what was the other example I gave earlier?
Nitrate.
What's that?
Aluminum nitrate.
Aluminum nitride.
Yeah.
Yeah, okay. So aluminum nitride, right? So in this case here, the charge on the aluminum ion is Al3 plus, right? That is this right here. And the nitride ion is N3 minus, right? So again, the number of plus charges is equal to the number of negative charges. So therefore, the formula is Aln, and that's it. Now, what if the charges are not equal? Let's say you're given, magnesium sulfide. So let me do that over here. Magnesium sulfide, right? So in that case, you look up the charge on the magnesium and you see that the charge is 2 plus. You look up the charge on the sulfide and you see that it's 2 minus, right? Oh no, that's a poor example. I'm sorry, it's not magnesium. I'm sorry. Let me use phosphide instead of sulfide. PHOSPHID. I'm sorry about that. So if you look up the formula for the phosphide ion, you see that it's 3 minus, right? So obviously the charges are not equal in terms of magnitude, right? So how do we get the charges equal? Well, in this case, what you do is multiply this by 3 and multiply this by 2. So that you're going to end up with a +6 total here, which will balance out the -6 total on this side, right? So the formula for this compound, when you put it together, will be Mg3 P2. In other words, these numbers here that I placed in front of the magnesium and the phosphide respectively becomes the subscripts in the formula. So therefore, this would be the formula for magnesium phosphide, right? And that's basically how you determine the formulas based on the name. And of course, if you're given the formulas, then you can determine the name. And that's what the first part of this assignment is all about. Let me clear this here. So basically in part A, you're given this table, you're given the combination of metal and non-metal here, and you're asked to do two things in each case. You're asked to determine the formula for the compound, and you're asked to determine also the name. So basically what you're going to need is a table that I showed you earlier, right? You need to refer to that table, okay? So in the case of the combination of beryllium and fluorine, if you go to the table, you'll see that beryllium will have a +2 charge, and the fluoride ion will have a -1 charge. All right. So as I said before, you need a molecule, not a molecule, you need a compound to be electrically neutral, which means that you need the number of plus charges to be equal to the number of negative charges, which means that you need to multiply this by 2, right? And then when you put this together, it becomes BeF2. All right, so that's the formula. And then the name of this compound would be beryllium fluoride. And that's it. And that's how you answer that question for the first line, all right? Any questions about this? Any questions? Any questions? Okay, so let me hear what you have to say about the next one. Potassium and sulfur. So look it up in the table, and I want you to tell me what's the charge carried by the potassium ion and the charge carried by the sulfide ion.
Potassium is K plus.
K plus, right, +1 charge. And what about the sulfide?
-2.
-2 or 2 minus, same thing. Okay, so what's the next step? Yes, sir.
You would multiply potassium by 2.
Multiply potassium by 2, so therefore the formula becomes
K2.
K2
S.
S. And what's the name?
Potassium sulfide.
Potassium sulfide. All right, very good. All right, let's hear what you have to say about the next one. Lithium and oxygen. So what's the charge carried by the lithium?
1.
+1. And what's the charge carried by the oxygen or the oxide ion?
-2.
-2 or 2 minus. So what's the next step? Multiply lithium by 2. So the formula becomes
Li2.
Li2O.
Oh,
And the name is
lithium oxide.
lithium oxide. Okay, the next one, sodium and selenium. So what are the ions?
+1.
Hmm?
Na has +1.
Oh, Na, okay, Na has +1. And what about the selenide ion?
-2.
-2. So what's the next step?
Multiply Na by
Okay, so this becomes
Na2.
Na2 Se, and the name is
Sodium selenide.
sodium selenide. Very good. Okay, magnesium and sulfur. So what are the ions in the case of magnesium and sulfur? And by the way, you guys out there in Zoom, please feel free to chime in. In fact, I think there's only one person out there by Zoom. All right. So what's the charge on the magnesium ion?
+2.
+2. And what's the charge on the sulfide ion?
-2.
-2. So what's the resulting formula?
MgS.
MgS. And the name would be
Magnesium sulfide.
magnesium sulfide. Okay, very good. All right, so basically, if you understood what we just did for the first 5 here, then you should be able to do the rest of that section. So I'm gonna leave that section for you to complete. Of course, if you have any problems while doing that, please feel free to contact me. Let's see here. All right, so I'm gonna just move on to part B. Now, part B deals with binary ionic compounds, but there's a slight modification or slight difference between some of these that we're gonna do and the ones that we looked at earlier. Because what you'll find, and if you watch the videos, you'll see that this is covered. What you'll find is that there are certain metallic atoms that can form ions of different charges. All right, just to mention maybe 1 or 2 examples. For example, in the case of chromium, right? And the formula for chromium is Cr. It turns out that there are 2 types of chromium ions. And there's actually more than 2, but I'm just going to mention these 2. One is Cr2 plus, and the other one is Cr3 plus, right? So basically, when it comes to naming compounds containing either of these ions, you have to indicate which ion is in the compound, in the name, right? So there are 2 systems that have been developed by IUPAC for dealing with this situation. One is called the stock system, and the other one is called the classical system. The stock system is actually easier to understand because in the stock system, basically when you're writing down the names of these ions, you indicate the charge by putting Roman numerals beside the name of the particular element. So in the case of Cr2 plus, the name of this ion would be chromium 2, while the name of this one would be chromium 3. All right, so that's the stock system, right? And you have some others like iron 2, iron 3, copper 2, copper 1, and so on, right? So that's the stock system. Very easy to understand. Basically, the charge in the formula would be the Roman numerals in the name, in parentheses, right? Now, the one that's more challenging, which is still used in chemical literature, is the classical system. And that one is a bit more challenging because you cannot tell directly what the formula or what the charge would be based on the name. I'm going to apply it to this one right here. So according to the classical system, this is called the chromous ion. And this is called a chromic ion. All right. So as you can see from the name, chromic ion. All right. So as you can see from the name, you cannot tell exactly what the charge is, right? The only thing you can tell from the name is that the one that ends with "ic" has one higher charge than the one that ends with OUS. That's all you can tell. You cannot tell directly what the charge is. So that's why the stock system is used more often than the classical system. All right. So whenever you have that situation where you have the possibility of a particular metallic ion can display more than one charge, you have to indicate the charge in the name. All right. Either by using the stock system, which is easier, or you can use the classical system, which is not as easy. All right. Now, let's apply that to solving the problems that we are presented with in part B. So let me clear this here. And let's move on to part B. So in the case, so basically you're asked to name these compounds, right? So the first one, they gave you CaCl2. What I would do is consult the tables and I'll look up the formula for, or I should look, well, I'll look up the formula for the calcium ion and see what the name is. And the name is, of course, calcium. Right? And then for the chlorine, that will be chloride. And that's it. All right? So the name of that compound is calcium chloride. So that one is relatively easy. Now, this one here is a slightly bit more challenging because they gave you iron and they gave you the nitrogen, right? Now, iron, if you look in the tables of the ions, you see that there are 2 forms of iron ions, right? One carries a +2 charge and the other one carries a +3 charge. So the question now becomes, which one is it? And the key to answering that question is to look at the charges carried by the two nitride ions, right? So if you consult the table again, you see that the nitride ion carries a 3 minus charge, right? And because there are two of them, that means that the total charge carried by the two nitride ions would be -6, right? Now here, you have 3 iron ions. Question is, what's the charge? Well, we know that because this is -6 total, that means the 3 iron ions will carry a total of +6, right? Which means that each iron ion will carry what charge? If 3 of them carries a +6 charge, then each of them will carry a +2 or 2 plus charge, right? So that means that the charge carried by the iron in this compound would be +2, right? So therefore, the name of this compound would be iron 2 nitride. All right? And that's how you determine the name based on the formula. All right? Any questions about this one? Any questions? Okay, let's look at number 3. In the case of number 3, they gave you TiBr3. And again, titanium, like iron, can display more than one charge, right? So again, you have to figure out what that charge is by looking at the charge carried by the bromide ion. So what's the charge? Hold on, let me what's the charge carried by the bromide ion?
-1.
-1, and there are 3 of them, right? So what does that mean for the titanium ion? What charge is carried by the titanium ion?
There's 3.
+3. So therefore, the name of this compound would be titanium 3, oops, 3 bromide. All right. Okay, very good. What about number 4? What do you think the name of that compound is?
Copper 1 phosphide.
Copper 1 phosphide. Do I need to explain this? Do I need to explain this one? No? All right. What about number 5? What do you think the name of that compound is? Excuse me.
4 selenide.
10, oops, 10, 4 selenide, exactly. Okay, very good. What about number 6?
Gallium arsenide.
Ah, sure about that? Actually, wait a minute, gallium, hold on, maybe I got it wrong, because so let me see, where's gallium here?
Gallium is GA.
Let's see, gallium. Oh, yeah, I guess gallium can only display one charge. So you're right. So let me go back to here. So it would be gallium arsenide. Okay, so again, if you understood what we just did here, you should be able to do the rest of that section. Now I think below. Oh, so below you're doing the reverse. So let me clear this here. So below you're given the name and you're asked to write down what the formula is. All right. So what do you think the formula for chromium 6 phosphide is?
Pr3P6.
Pr3P6. Not quite, because they need to have the lowest. What's the term they use?
Oh, yeah.
The lowest I forgot.
So it would be CrP3.
Right, exactly. You divide both of these by 3. So that would be Cr P2. Oh, wait a minute, hold on. Yeah, CrP2, yeah, okay. What about the next one? Vanadium 4 nitride. What do you think the formula for that compound is? Vanadium 4 nitride. So this tells you that the charge is on the vanadium ion, that's +4. And then you have nitride. What's the charge on the nitride ion?
-3.
Okay, so V4 and then N3 minus. So what do we do next?
Multiply B by 3 and nitrogen by 4.
Okay, so when we put this together, it becomes what?
B3 and 4.
B3 and 4, very good. All right. What about the next one? Tin 2 sulfide. Tin 2 sulfide. So the charge on the tin is 2 plus, and what's the charge on the sulfide?
-2.
-2. So when you put this together, it becomes,
ENS
I'm sorry,
would be, S and S.
S and S. Okay, very good. Cobalt 3 oxide. Cobalt 3 oxide.
CO2O3.
Hint, hint. Oh, you mean the formula? I'm sorry, I thought you meant the charge. Okay, my bad. You said what? CO?
CO2O3.
Oh, okay, that's correct, actually. Yeah, I thought you were, all right, good. I thought you were mentioning the charge. Okay, CO2O3. Okay, very good. All right. And let's see here. Let me clear this here. Okay, titanium 2 selenide. Titanium 2 selenide. What's the formula?
TISE.
TISE. Okay, so I'm gonna leave the rest of that for you to do as well. So let me clear this. Let's go down. Okay, now we're going to get into, so we're just dealing with binary ionic compounds and how we name them, right? So what we're going to get into now is a discussion of what we call binary molecular compounds. Binary molecular compounds, which are different from binary ionic compounds. Now, what they do have in common is that they both consist of 2 elements in each case, right? But the difference is that in the case of the binary molecular compounds, the 2 elements must be nonmetals, right? So in the case of binary ionic compounds, you have a metal-nonmetal combination. In the case of the binary molecular compounds, you have a combination of 2 nonmetal, right? So now things are a bit different in terms of the rules, for a couple of reasons. One of which is basically, how do you determine which element comes first in such a situation? Which element comes first in the name and in the formula, right? And the answer is, as stated here, is that the one that is more metallic in character would be mentioned in the name and formula first. So how do you determine which one is more metallic? You look at their relative positions in the periodic table. The one that is further down and to the left of the periodic table would be the one that is more metallic. So for example, if you're given a combination of, let's say, I don't know, let's say magnesium and selenium, right? Well, no, I'm sorry, non-metals. Bad example. Let's say you're given, well, since you're next to each other, nitrogen and oxygen, right? 2 non-metals, right? Nitrogen would be mentioned first, followed by oxygen, because nitrogen is to the left of oxygen. Or if you're given, let's say, bromine and chlorine, right? They're both in the same group, right? So in that case, bromine will be mentioned first, then chlorine. All right. So that's basically how you determine which element comes first, right? The element that comes first in the name and in the formula would be down a group and to the left of a period. All right. Okay, so based on what we have just discussed, let's see if we can answer question number 1. It's saying, which of the following nonmetals would you write first, assuming you're writing the name of the compound? So you have oxygen or nitrogen. So which one? I don't know if I can here. Oxygen or nitrogen, which one would be indicated first?
Nitrogen.
Okay, very good. Iodine or chlorine?
Iodine.
Iodine. Silicon or sulfur? Exactly. All right? And that's it. Okay, very good. Now, the next question has to do with another difference between naming ionic, naming binary ionic compounds and binary molecular compounds, right? And that is in the case of binary molecular compounds, you have to use prefixes to indicate the number of atoms of each element present in the particular compound. And there are some exceptions which we're going to talk about later on. But basically, that's one difference. And the prefixes, just in case you missed it when I gave you those video lectures. Mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. And we can actually go beyond 10, but for our purposes, that's where we're going to stop, right? So these are the prefixes that you're going to use when you're naming binary molecular compounds, right? So you have to use these to indicate the number of atoms of each element present, all right? So what I just said is actually an answer to question number 2. Why is it necessary to use prefixes in the names of covalent compounds in order to indicate the number of atoms of each element that is present in a molecule of that compound, right? So that's the answer for number 2. You use prefixes to indicate the number of atoms of each element present in a molecule of the compound. All right. So with question 1 and 2 out of the way, whoops, let me clear this first. And scroll down. Okay, now this question has to do with some exceptions to the rules that I just mentioned. This question is asking, in what cases we do not use prefixes when we're naming these compounds? And I'm just going to write down the answer here and explain using examples. So there are 2 situations where you do not use prefixes. The first one is if the first element in the name or compound, I'm sorry, in the name or formula, I should say, in the name or formula, has only one atom represented. All right? So if you have a formula and there's only one atom for the first element, then you do not use mono. So let me give you an example. This compound here is called carbon dioxide. All right? There's no mono here indicated for the carbon. There's a di indicated because you have 2 oxygen, right? And one more thing I should mention, which I probably didn't mention before, the IDE ending is also should be in place, right? Just as in the case of binary ionic compounds, right? So this is one example where the first element in the name and in the formula has only one atom. So therefore you do not use mono to indicate that there's only one atom, right? Another example, if you're given something like this, SF6, the name of this compound would be sulfur hexoxide. And let me just say something about this too, right? According to IUPAC, you could also say hexaoxide, right? So if you say hexaoxide or simply hexoxide, both are acceptable according to the IUPAC rules, all right? Okay, so that's the first instance or the first exception to the use of prefixes when naming these compounds. The second exception is if the first element in the name or formula is hydrogen, then no prefixes are used whatsoever. No prefixes are used whatsoever for either element. Use whatsoever. All right, so let me give a couple of examples. So if you're given something like this, HCl, right? The name of this compound is hydrogen chloride. And that's it, right? So not monohydrogen monochloride, right? It's just simply hydrogen chloride. Or if you're given this, right? The name of this compound is hydrogen sulfide. Hydrogen sulfide, right? So it's not dihydrogen sulfide, just simply hydrogen sulfide, right? So those are the only two examples when it comes to naming binary molecular compounds, right? One, if the first element has only one atom represented in the formula, then you do not use mono to indicate the number of that particular atom. And then secondly, if the first element is hydrogen, right, then no prefixes are used for either hydrogen or the other element, right? And that's basically the two exceptions that you need to be aware of, all right? Apart from that, you need to use prefixes otherwise. So let me clear this here and scroll down. Okay, so basically, we're going to apply what we just learned to answer these questions, right? So they gave you the names first, and you're asked to write on the formula, and then the second half it's the reverse, right? Okay, so what would be the name of, I'm sorry, what would be the formula of iodine heptabromide? Iodine heptabromide. IBR hepta. What does hepta mean?
7.
7. IBR 7. Okay, very good. Dinitrogen pentoxide. Dinitrogen pentoxide. Dinitrogen pentoxide.
N2O5.
N2O5 is indeed correct. Silicon tetrabromide. Silicon tetrabromide.
SIBR3.
I'm sorry?
SIBR3.
Tetra? What does tetra mean?
4.
4. So it's SiBr 4. All right? Dichlorine monoxide. Dichlorine monoxide.
Yeah.
Cl2O, okay? Sulfur hexafluoride. Sulfur hexafluoride. And, well, fluorine doesn't have L, it's just SF. So, but you're right about the 6, so it's SF6, all right? By the way, that's a common error that students make. Diphosphorus hexaiodide. Diphosphorus hexaiodide.
P2I6.
P2I6 is indeed correct. Okay, tricarbon disulfide. Tricarbon disulfide.
T3S2.
Very good. C3S2. Tetraphosphorus decoxide. Tetraphosphorus decoxide.
P4.
E4.
O10.
O10 is indeed correct. Very good. All right. So the rest of it is the reverse. So let me clear this first. Let's go down. So it's a reverse. Now they've given you the formulas and you're to give the names. All right. So let's start off with SO3. What would be the name of this compound?
Sulfur trioxide.
Sulfur trioxide is indeed correct. Next one. XeCl4.
Xenon
Xenon
tetrachloride.
tetrachloride is indeed correct. All right, very good. Next one, Br3O8. Br3O8.
Tribromide.
Tribromine. Tribromine what?
Octoxide.
Octoxide or octaoxide. Again, this is one of the possibilities allowed by by IUPAC, you can say octoxide or octoxide, all right? N2F2, dinitrogen difluoride. Difluoride. Okay. And then ICL5. ICL5. ICL5.
Iodine.
Iodine or iodine
Pentachloride.
pentachloride is correct. Okay, very good. CF4. CF4. Carbon tetrafluoride is correct. And then the last one, oh, that's too easy. What's the last one? Carbon what?
Oxide. Is it
Cool.
monoxide?
I'm sorry? Monoxide. All right, and that's it. All right, very good. Okay, so that's basically how you name binary molecular compounds. So remember the two exceptions when you're doing these problems. All right. Let me clear this here and scroll down. Let's see what's next. Oh, some more. In this case, we're writing down the formulas. You know what? I'm going to leave that for you guys to do. You guys should be able to handle it. All right. So again, if you have any problems, let me know. But you should be able to handle these. All right. So let's go down. Oh, and you should be able to handle these as well. It's a reverse. They gave you the formulas and they're asking for the names. All right. So again, you can handle that. All right. And let's see what next. Okay. So now we get to probably the most challenging part of naming compounds. All right. At least at this level. So we have a group of compounds known as acids, right? Simply put, acids are compounds which, when added to water, produces hydrogen ions, right? Now, the rules for naming acids are dependent on the kind of acids that you're dealing with. So we're going to start off with a discussion of the binary acids, right? Which I covered in the videos, but I'm just going to go through a quick review of how do we name acids, right? Now, when it comes to, okay, how am I going to introduce this? Okay, I'm just going to go directly into one example. So this compound here, HCl, is normally a gas, right? Under normal, conditions, right? And based on what we have learned so far in terms of naming binary molecular compounds, this is called hydrogen chloride, all right? Hydrogen chloride. Now, if you were to take this gas and dissolve it in water, you're going to get your acid solution, HCl aqueous, right? Now, the name of this, because it's acidic, will be different from this here. And I'm just going to give it a name and then I'll explain how we arrive at that name. The name of this solution is hydrochloric acid, all right? So please note how the name is structured. All binary acids, oh, by the way, we're talking about binary acids here. So let me just put that here. Binary acids, right? So when it comes to naming binary acids, they all start with hydro, every one of them. They all start with hydro. Then you have the stem of the name of the other element, which is chlorine. So we put chlor here, right? And then this part of the name ends with ic acid, right? So for binary acids, it's hydro, then the stem of the name of the other element, then ic acid, right? Hydro, the stem of the name of the other element, then ic acid. Let me give you another example. H2S gas. This is called hydrogen sulfide, a very awful smelling gas. In fact, the odor of rotten eggs is basically hydrogen sulfide, right? So this is hydrogen sulfide, right? And if this is added to water, right, this becomes H2S gas. So the name of this compound is, or the name of this, I'm sorry, not gas, aqueous. What am I saying? This is aqueous. So, aqueous, right? So the name of this acid is hydrosulfuric acid. All right, so again, you see how the name is structured. You have hydro, then sulfur, which is actually the full name of that element, and then it ends with ic acid, right? So it's hydrosulfuric acid, all right? So if I were to give you this, which is hydrogen selenide, and I add this to water, then what do you think the name of that compound is? Or let me write down the formula first. H2SeAQ, right? That's the formula. So what do you think the name of this acid is? Hydroselenic
Acid.
acid. All right. So that's basically how you name binary acid, right? Hydro, then the stem of the name of the element, followed by ic acid. All right. So this is binary acids. Now, another group of acids that we need to learn about are what are known as oxyacids. And as the name suggests, oxyacids contain hydrogen, oxygen, and one other element. One other element. All right. So again, I'm just going to go directly into a couple of examples. So one example of an oxyacid would be HNO2, right? Now, let me explain using, there's several approaches you can take. I think this is the best approach, so let me just go right into it. Now, the approach I'm going to take is showing you how to name the acid based on its corresponding anion. And these anions can be found in the table that I've given you before, right? So in the case of NO2 minus, this is called the nitrite ion, all right? And to go from the nitrite ion to the corresponding acid, you add an H plus, right? So when you add H plus to this, you get this acid, right? Now, the name of this acid as a result would be nitrous acid. All right? So basically, the name of the acid is derived from the name of the anion from which it is formed. In other words, in this particular case, we replace the ITE ending with the OUS acid to get the name of the corresponding acid, right? So nitrite ion becomes nitrous acid when you add H plus. Let me give another example. This particular ion here is called the sulfide ion, right? Now in this case, because you have two negative charges here, you need to add two H plus ions, and the resulting acid would be H2SO3. And the name of this acid would be sulfurous acid. All right, so again, we replace the ITE ending with OUS to get the corresponding anion, I'm sorry, the corresponding acid name, all right? So IT becomes OUS, right? But there's yet another group of ions where the ending of the names end with ATE. So let me do a couple of those here. Let me get rid of here. Okay, so this one here, this first example here, is the nitrate ion. NO3 minus, this is called the nitrate ion. All right, so to get the corresponding acid, we add H plus to it, and that gives you HNO3, right? Now, in this case, because this is nitrate, the name of this acid is nitric acid. All right, so you see here what we did was that we replaced the ATE ending with ic acid. All right. Here's another example. SO4 2 minus. This is known as the sulfate ion. Right? In this case, you need to add two H plus ions here to get the corresponding acid, which is H2SO4. Right? We have two H plus here because we have two negative charges here, right? The name of this acid is sulfuric acid. All right? And that's basically how we name these acids based on the name of the corresponding anion ending with ATE. The corresponding acid name would be ending with ic acid. So if I gave you something like this, which is known as the phosphate ion, right? In this case, you have to add three H pluses because you have three negative charges to get H3PO4. So what would you say the name of this acid is?
Phosphoric acid.
What did you say?
Phosphor.
Well, it's actually phosphoric. I can understand why you say that, but it's actually phosphoric. Phosphoric acid. All right. So that's basically how we name acids based on the name of the corresponding anion. All right. Now, there's one particular acid which is kind of unique to all these here. And all the ones that we have discussed. It's very different from all the ones that we have discussed before. So let me clear this here and write down the corresponding. Let me write down the formula for that acid. The formula for this acid is HCN aqueous, right? Now, the reason why this is a bit unique is that it's not a binary acid. As you can see from the formula, it's made up of three elements, right? So it's not a binary acid, and it's not an oxo acid because there are no oxygens present. So the question now becomes, how do we name this? So what the powers that be decided, the IUPAC folks, what they decided was that they're going to treat this as a binary acid, right? So basically, the corresponding gas that you have to add to water is this: hydrogen cyanide, something you don't want to inhale unless you're contemplating suicide, right? So when you add this to water, so this is a gas, right? So when you add this to water, you're going to get HCN, and the name of, because they're treating this as a binary acid, the name of this is hydrocyanic acid, right? Even though it's not a binary acid, but the rules for naming binary acids are applied to this, right? If you remember, we said that all binary acids starts with hydro, then the stem of the name of the element in between, and then ic acid. In this case, it's two elements, which is called the cyano group. So therefore it's called hydrocyanic acid. So that's a bit, unique when you compare to all the other acids, right? And that's basically the rules for naming acids. So with that said, let's at least if we can name the first couple of these, or write down the formulas for the first couple of these. So what would be the formula for nitric acid?
HNO3.
HNO3 is indeed correct. What's the formula for chloric acid? Now remember, you have to go to the table and look up the formula for the chlorate ion, right? And then based on that, you can determine what the formula for chloric acid is. So based on that, what would be the formula for the chloric acid?
HClO3.
HClO3 is indeed correct because the chlorate ion is ClO3. Oops. The chlorate ion is ClO3 minus. So you have to add an H plus to that to get the formula for the chloric acid. Acetic acid. Acetic acid. So you have to look for, in the table, you have to look for the acetate ion. So what's the formula for the acetate ion?
C2H3O2.
C2H3O2 minus. So therefore the formula for acetic acid is
H.
HC2H3O2. Very good. Hydrobromic acid. Yes, sir.
HBr. AQ.
Exactly, HBr, AQ, and that's very important. You have to put the aqueous state symbol, because if you just simply put HBr, then we're going to assume that it's not aqueous, it will be a gas, in which case it would be hydrogen bromide, right? But because you put the AQ there, that makes that hydrobromic acid. Okay, what about sulfurous acid? So what would be the corresponding anion that you look for in the table? What would be the corresponding anion that you look for in the table? Hmm? No, we're talking about sulfurous. Yeah.
Sulfide?
Sulfide, exactly. So SO3 2 minus. So how do we get from sulfide to sulfurous acid?
The H.
Two H pluses, right, exactly. So the formula becomes what? H2SO. H2SO what? 3, exactly. All right, very good. Okay, so again, I'm gonna leave the rest of that for you to do. Let me just scroll down and see what's. Okay, now this one is the reverse. All right, so let me clear this here. Okay, so let's deal with number 16. What will be the name of this compound? Now, what I would do in this case is that I would go to the table and look for the name of the ClO4 minus. Right? And what's the name of the ClO4 minus? I'm sorry?
All right.
No. ClO4 minus perchlorate. Perchlorate. Okay, so if the formula, if the name of this ion is a perchlorate ion, then what's the name of the acid? Perchloric acid, exactly. Perchloric acid, very good. Okay, what about number 17? I think I did one for you already. H3PO4. So what would you look for in the table? PO4 3 minus, right? What's the name of this ion? Phosphate. So what's the name for H3PO4? Phosphoric acid. Okay, next one, HCl aqueous. Binary acids. What do all binary acids start off with?
Hydro.
Hydro. So what's the name of this acid?
Hydrochloric.
Hydrochloric acid. Very good. Okay, the next one, H2SO4. H2SO4. What would be the anion you look for in that case? In the table. SO4 2 minus, and the name of that ion is sulfate. Okay, so what would be sulfate? Okay. So what would be, oh, I spelled sulfate in British way. Not the American way. My apologies. Sulfate with an F, that's the American way. Right? The British way is PH. Okay, so where am I? So what's the name of the acid? Sulfuric acid. Okay, and then number 20, HNO2. HNO2. What would be the formula you look for in the table? NO2 minus, and what's the name of that ion? Nitrite. Okay, so what would be the name of this acid? Nitrous acid, exactly. Nitrous acid. Okay, so again, I'm gonna leave the rest for you to do on your own. What time is it? Okay, 15 minutes to the floor, so.
Right here. So, it's still basically game.
Okay, Okay, so this is just some miscellaneous acids and bases, in terms of names and so on. The bases are very easy to name. They're basically, you can name them based on the rules that we learned for ionic compounds. So I'm gonna leave that for you to do as well. Again, if you have any questions, please feel free to contact me. All right, so that's pretty much, so, that's not pretty much it, because there's another miscellaneous addendum, which I think is a part of the handout that I've given you as well.
Yeah.
And so those of you guys out there in Zoom, let me see who's out there in Zoom. Okay, there's only one person out there in Zoom. There are two links in the I'll show you where it is. One for the original handout. That is this here, chapter 5, and then chapter 5 addendum, that should be included as well, right? So for those of, well, for the one person who's out there in Zoom, make sure that you download this one as well. And you guys should be able to do this. Let me just check this here. You guys should be able to do this one as well. It's basically a mixture of the different types of compounds and how you name them based on all the rules that we have covered, all right? So what I'm gonna do right now is set up a Dropbox for this. So this is assignment 5. And let me do this. Okay, so. Okay, so I'm going to set the 14th as a deadline. And that's because you guys have the test to prepare for and all that stuff. Being generous. So let me do this. So available then. And do this. Okay, so 14. All right. So now you should be able to submit your assignment number 5 in that Dropbox. If you have any problems between now and then, please feel free to call me. So let me just remind you about the test in the testing center. If you have not signed up for it yet in terms of making an appointment, do so now. I think I emailed you or posted an announcement about what you should see on the very first page, right? If your test does not have that, let them know that's what you're looking for and that's what you expect, all right? Also, you should each be given a copy of the tables, right? And the reason why I'm mentioning all of this is because in the past, I've had issues, especially last semester, where students, for example, I remember one student ended up with only half the number of pages when they went to do the test, right? Another student was not given the tables and all that. So make sure that you let them know that I said that you should get the tables. What else? There was another issue. The only thing you need to bring are a pen and calculator. You should also be given a sheet of scratch paper. And what else? I think that may be it, all right? So so make sure that those things are seen. As far as going back to what I said about the first page, please look for spring 2026, right? Because one of the problems that I had from previous semesters is that they somehow dig up some past tests that I have given before to the students who are currently doing a different test, right? So look for spring 2026. If your test paper does not have that, then that's not your test paper. And just let them know that you should be given the one with that at the top, all right? And I think that's it, unless there are any questions. Any questions? Any questions? Yes, ma'am.
When you say tables, you mean the conversion table, the periodic?
Right, exactly. Periodic table, conversion tables, list of ions, all that. That's in one package.
Thank you.
So that should be given to you. If you don't get that, make some noise. But don't make noise. Let them know that you're expecting that, right? And if you have any issues like, you know, what I just mentioned, just send me an email and then I'll have to talk to them forward, right?
Yeah, let it go in. Okay.
We do, take care. Yes, ma'am.
Does that cover chapter 1 to 5?
No, I should have mentioned that 1 through 3. Because, yeah, you won't be tested on 4 or 5. Right, yeah, 1 through 3. I should have mentioned that too, yeah. We have until, Friday, yeah.
I think almost all the Friday dates,
That's it?
I think almost all the Friday testings, out already.
Oh, really?
Yeah.
Have a good day.
Yeah, you too, take care. Okay, on to my last class for today. For Southeast.
Was it Camp 2045?
Yeah, lab.
Have a nice one.
Yeah, you too, take care.